Introduction and purpose. This lab is intended to compare the experimental and observed result of a constant velocity experiment to the computed and predicted result of the same experiment modeled in GlowScript. It is also meant to demonstrate Newton's second law. For this lab, constant velocity is defined as the same speed in the same direction. For this lab, I used a car, which is our system, with a single push at the start to complete the experiment. The surroundings is everything else, like the table and air. Software used for analysis. I used Tracker to break down into time intervals for my calculations and for our observed data, and I used GlowScript to create a model for the expected outcome. In this experiment, I found that it actually doesn't have a constant velocity, but actually slows down at the end, and it starts a bit faster than the computed outcome in the beginning. This is my tracker data and the video. These are my equations and calculations. To start, we needed to find the initial velocity, which is where I subtracted the second position from the first position and divided that by the change in time, yielding a 0.758 meters per second velocity in the positive x direction. Using this velocity, I constructed the velocity update formula, which is v final equals v initial plus F net over mass times delta t. In this case, our v final should equal our v initial because F net should be 0, which would cancel out everything to the right of the plus sign. Using this, I calculated the position update formula, which is R final equals R initial plus V average times delta t. For this, V average should just be V final, because V final plus V initial divided by 2 is just going to be V final. This is the results I found. The light blue is our tracker observation, and the dark blue is our GlowScript predicted outcome. As you can see, the dark blue is linear, while the light blue is a little bit more curved. The light blue surprisingly outpaced the dark blue at the in the middle. I was very curious why, because it shouldn't have gone faster than the predicted outcome until I realized the surface that I actually used to push the car was not level and it was actually going downhill. This is our GlowScript analysis and code. The top code initializes the vector starting position and the initial velocity. It also sets delta t to be 1/30th of a second, which would be one frame of the 30 FPS camera I was using. And also the time the initial time was set to 0.1 seconds because that was the first time period that I felt comfortable that I wasn't still pushing the car. The bottom code sets fnet to 0, which is the entire purpose of the lab, showing a constant velocity, which would have no net force. It also runs the position and velocity update formulas for each data point in the while loop, which is just our iterations. Possible errors and what ifs. Possible errors include forces that do not equate to fnet of 0, rounding errors in calculations that could compound over time, creating errors, center of mass not being perfectly chosen for each point, leading to more discrepancies, and the fact that the table was tilted, like I said earlier. What would happen if the negative x and positive x directions were switched? Well, the slope would just be negative instead of positive. And if our fnet wasn't 0, in actual observation, it really wasn't, as can be seen of it accelerating and decelerating. There was some air resistance and friction causing it to slow down, plus the force of gravity shifting the car downhill.